All right, our last talk before the break is going to be given by Jeff Thayer from CU Boulder. It's the last tutorial of the workshop and entitled Plasma Neutral Interactions in the MLT-X, which is the altitude range between 80 and 200 kilometers.
Thank you, and good morning. The last talk, the last day of a long week. There's something a little bit intimate about it because you all had an option to be here today or go home early or catch a flight, and I appreciate you staying here for this last talk, and it is something that as a tutorial I'll try to make basic descriptions that hopefully can be used more broadly rather than a specific research topic. And so this one is with regard to plasma neutral interactions, and it follows off of what we've been defined as a grand challenge in the CEDAR community, which is what we're calling the MLT-X, or the extended mesosphere lower thermosphere, basically covering an altitude from 80 to 200 kilometers. We've identified that domain as being a challenging one, and one that we've had a workshop for the past 3 years. We'll have a fourth workshop again after this session. So I encourage you to come to that as well. We had a tutorial lecture last time back in 2014 to kick off the Grand Challenge by Tim Fullerell, and so he talked about the wave element of the challenge. Now I'm going to talk about the plasma neutral interaction portion. The universality of plasma neutral interactions is something that makes the topic addressable to many disciplines. For us, it's more in this planetary space-atmosphere interaction region. Interestingly enough, there's the plasma neutral interactions at stellar chromospheres is also highly relevant to our own physics. Dusty plasmas, the introduction of neutrals and of dusty neutrals as well as plasmas. And then also just the relationship that these interactions have in determining the planet's habitability, or even recently people are talking about interstellar space weather and the exoplanet evolution with regard to the plasma neutral interactions that must be taking place there. So I'll go over a few topics regarding our own space-atmosphere interaction region, what we called in the CEDAR document as the SAIR. That region is a weakly ionized gas. I'll talk about the transport equations that are appropriate for the region, ionospheric plasma motion, leading to conductivities, currents, and I'll talk a little bit more about frictional heating and heating rates. And then I'll talk about a study that we did with the colleagues during an LWS work program about the chromosphere and how it related to our Earth's ionosphere. So just to get it going, with regard to plasma neutral interactions, we're really discussing a number of topics, potentially. I won't cover these. I'll talk about something more specific, but you can think about it as the chemistry is a plasma neutral interaction when we have plasma interacting with neutrals and recombining or causing glow. There's also the drag forces associated with plasma neutral interactions. There are the frictional heating elements that plasma neutral actions contribute to, and then also the electrodynamics. And so all of these are plasma neutral interaction elements that hopefully from my tutorial you can relate the descriptions to these various aspects. So in defining our plasma is the first step that we should take when trying to determine how are we going to describe the plasma. So here's our diagram of both neutrals as well as charged species in the upper atmosphere. And clearly the neutral gas is the dominant, is dominant over in terms of concentration with regard to the plasma. So a definition that's universal is people define plasmas as either weakly ionized, partially ionized, or fully ionized. And in so doing, it really casts the equations that are most applicable to that particular problem. So we should do the same. I've done that here by casting it below about 250. The electron-ion collision interactions are much less significant than the electron-neutral and ion-neutral interactions. And so below 250, we're working in what's called a weakly ionized gas. And that's usually defined by plasma physicists. But if you're a hydrodynamicist, you might say this is a strongly neutral gas. And this is where hydrodynamics and electrodynamics or plasma physics combined. And it's an interesting domain, not only by the physics, but also by the people that you interact with in trying to describe this region. Because people come from different perspectives, and I'll talk more about that throughout this talk, actually. So above 250, we have the Coulomb interactions start to become important, and you have to include both. And that actually makes the equations a little more coupled and a little bit harder to handle, honestly. So, and so for today, we're going to focus on the weakly ionized gas, the region below 250, the region that we're defining as the MLT-X. Okay? So we need to set up our system of equations that we're going to use to define our domain. Now, that's, if you're a modeler, that's very important for developing the model. But you have to also set up your equations, whether you're someone observing the scene as well as taking data. You need to understand the system of equations that apply. And so first that we recognize is that ion-neutral coupling is strong, and that we need to include both the neutral electron and ion species in describing it. We can start from the most fundamental equations that work from the velocity distribution functions of a particular species, and therefore you can start with Boltzmann's equations and start working your way down through to derive the general transport equations. I won't do that today, but we will cover, we will recognize that a number of these equations are derived from that method to get to the formalisms that we use to apply. Now, when you get to the point of those equations are rather universal, but now when you get to your system, when we're talking about below 250, and we have to solve the Boltzmann collision integral, you start talking about the collision domain. Which collision domain do we lie? Because that determines how the Boltzmann collision integral will be solved. And in our case, we're in a dense gas with a weakly ionized gas, and we result in a Boltzmann collision integral that's actually can be quite complicated, but has been applied quite simply to Maxwell collisions that is described more heavily if you want to look at Schunk and Nagy's book, for instance, as a good place to delve into that. But effectively, we need to make the system specific, then we need to consider these collisions as well as the domain, or the, I should say, the velocity distribution function that's used to build these equations. You need to define the velocity that dictates your system. I'm going to make this point over and over again because it's actually an important one in trying to communicate between communities, because that's a complication that leads to confusion. So our system of equations, and like I said, we can go to Schunk and Nagy, and we can go and we can take our velocity moments of the Boltzmann equation that leads us to various forms of the description of our system. Essentially, we get down, for our application, the 13th moment approximation, where 13 refers to the number of variables required to be defined in order to describe the system, being number density, the three components of a neutral wind, the temperature, the heat flux vector, and and a symmetric stress tensor. So that adds up to 13. That gives you 13, and it gives you a description of our system. And we've worked through this, and we've said this is what we need in order to describe the environment. And this is close. You know, you can get, if people are familiar with the Navier-Stokes equations, it's effectively drawn from this in slightly different approximations on the heat flux vector and the stress tensor. However, we do have a plasma, and we also need to not only describe the gases, but we also need to look at the coupling that can occur from a plasma perspective, and that means we need to use Maxwell's equations. With Maxwell's equations, of course, we'd like to keep the time dependencies, but oftentimes in ionospheric applications, we simplify to the electrostatic form. And there are some challenges with that. Well, it's a simplification that leads to help in the formalism. It makes it challenging when you go to describe processes that may involve more electromagnetic activities than electrostatic activities. And in that regard, you would want to keep your dBdTs and your dDTs in order to get the electromagnetic coupling together. But in most applications in the region that we're discussing, we have electrostatic applications. We can derive a conservation of charge, and in the ionosphere, we tend to set that to 0 because this happens very quickly in a matter of seconds. And that we also derive an ionosphere Ohm's law, by which we can describe our J in a relationship with E. And then therefore, we can now close our systems out and start to solve the equations. If you combine your Div.J equals 0 with plugging in the J here, you can get your dynamo equations, for instance, and those dynamo equations can be coupled into your other equations to describe the system. Okay, so 2 main points I want you to remember as I go through this talk. And it's really very general, but I find that when I do talk, and this is really spawning from talking to the Chromosphere community, where we really were on different planes when we just discussed plasma-neutral interactions, that we found that one thing we needed to just agree on was the coordinate system at which we're working in and the reference frame. So for instance, if you're using, so sometimes coordinate systems are defined for different reasons: physical, mathematical, numerical. For instance, just simply, we use pressure coordinates in a number of our models for our vertical coordinate. Some of that's physical, but also there's some numerical supporting reasons for doing that as well. And also, typically, we work in an Earth-fixed frame, which is a rotating reference frame. So that means we go ahead and define it, whatever that's going to be, but then we also need to understand it. And I think that's one of the other challenges, is that you can go ahead and define it, but do you really understand it? And so the physical interpretation is just as important as the mathematical or numerical. And so, for instance, an Earth-fixed frame is a non-inertial frame. Therefore, we have to account for non-inertial forces, Coriolis and centripetal accelerations that must be included in our form. If you're talking to somebody who's not working in that frame, you can be talking very differently and have a confusing conversation. The other thing is, as I mentioned, when we're doing the velocity distribution functions and plugging those in and working through, you are making an assumption about the velocity, the average velocity definition of your system. And these are important because as you take the higher moments, you have to include they affect the way you describe and define these terms. And this is particularly challenging with a multi-constituent gas, because a multi-constituent gas, okay, what velocity are we talking about? If I'm talking about the velocity of a molecular nitrogen molecule, and someone is talking about the velocity of an oxygen molecule, they're actually they have different masses, they have different thermal energies, they can be different. And so we need something to reference to, and it's that definition that I'll play on as well. So these are important points to think about as I go through. Now, we'll set up our system equations. This is just our momentum equations that are typically applied to our system. We have the neutral equation, the ions, and the electrons. And I would describe this as being a multi-fluid description of the system, where each of them have their own individual velocity distribution function description. So for the neutrals, we're going to have an average neutral velocity. Mind you, in our system, we have multiple constituents. So this is the center of mass neutral wind velocity. So that means that whatever species, the majority species, is really dictating what that neutral wind is going to be. So if you're a minor species, you're not going to be required to meet the goals that the major species needs to do in order to couple it back to the other equations. So that's important. Now, we have all of our terms in here that we've showed before. We need to include our ions. We need to include our electrons. And the key, of course, is the coupling that occurs between the collisional exchange between the neutrals and the ions and the electrons. So another approach that you could take is you could say, I'm going to take a single fluid approach. I'm going to sum up all these equations. I'm going to use a mass average velocity that represents the mass average between the neutrals, the ions, and the plasmas, and come up with one equation to describe that momentum description. And that's another approach. That approach is a different definition than what we're going to do here, and so it leads to some differences in describing how to go forward. So as I mentioned, the collision frequencies are key in the coupling between the plasma and neutrals, and of course, we have I'll focus largely on the ion neutral collision frequency and the electron neutral collision frequencies, and the relationship they have to the gyro frequencies. I've also had the pleasure of working with Art many years, and it was a pleasure to work with Art on this paper where we went back and did some ionospheric electrodynamics where we included some of the Poynting flux discussions at the time that we were having. But this is from that paper, and you know, we describe here again the neutral gas and the varieties that you can have with the electron density, which is important, but also the collision frequency, and then the relative gyro frequencies and the electron and ion gyro frequencies. Well, so if we go to our ion and electron momentum equations, and we're back to the same form we had before, where it includes all of these, the pressure gradients, gravitational, electric, magnetic, and collisional forces, it's very typical for us to take the step of assuming that the pressure gradient, the gravitational forces are not significant, and that we only use static and EB fields. This leads to forms of the equation that look something like this, where you have, in this formulation, how it's laid out, you can see that you can write the velocity, ion velocity in terms of orthogonal components in the reference of the E field, E cross B field, and then that along the magnetic field line. This is where we assume the neutral wind is 0, and we're going to start with that just to get acclimated. And we have the same expression for the electrons. I think we all know that it's used heavily in our community, that the plasma drift in the region where this mobility factor, which is the ratio of the gyro frequency to the collision frequency, when it's much greater than 1, the ions and electrons are going to more aptly be tied to a magnetic field line than they are going to experience a collision to be removed from that. And so therefore, we can call it a frozen-in flux. And I'm going to use some incoherent scatter radar data to kind of support this, just to tie observations with theory. I'm going to use a number of these types of graphs. Let me just describe these quickly for you. This is the altitude on this scale. This is time on this scale. These are slices at particular altitudes. And the way I want you to read these is that these vectors, these are not like the vertical direction. These are horizontal plasma drift measurements. And north is up and east is to the right. So just look at these as like, at a certain altitude, the horizontal plasma flow. And if you just look at, if we do this, when this happens, the equations break down simply to that. And if you look at like this case here, which I show in the black line here, so along this case, we can see that the northward directed flow, that's plasma flow, and that's in the E cross B direction. And now our E is defined in the east direction. And we're going to use this example for a few cases to illustrate how things evolve as we move from here being the F region down into that MLT-X region that we're interested in studying. And when we do that, we need to look at our ion momentum equation again, but now we can't assume that the collision, that the Ki quantity is dominant. And so what we find is that, of course, we're going to start to experience a collision as we come down in altitude. And the ions are going to collide sooner than the electrons are. Or I should say the ion is going to collide more frequently than their gyro radii. And the ion motion will start to go from an E cross B direction. So if we have B here into the board, E and E cross B, initially here we are, same velocity plasma drift. As it comes down in altitude and experiences collisions, as the collision frequency increases, this ion will rotate into the direction of E. And as we move down, the magnitude will also decrease and will rotate more and more into the direction of E. Well, you know that the difference between the ion vector and the electron vector equates to a current. And so currents, then, you can be looked at in a similar way. Plug in your momentum equation solutions that we just did before, get your currents. You can then see how the currents are generally, up in here, they're essentially 0 due to the fact that there's no differential velocity. And as you come down in altitude, now the currents are actually increasing and rotating away from the direction of E, eventually going into the minus E cross B direction. And in so doing, the current increases, but to a point. And that point is related not to the velocity differential, but to the electron density that's in front of that. So if we take a look at more incoherent scatter radar data, the same day as I did before, but now I'm looking at the lower portion and a higher resolution as well. And if we go back to that time where we saw we're above about 140, 150 to about 180, we generally see where the plasma is not really changing much with altitude, and you're still in the frozen influx. But then things start to get a little slushy when you get down lower, because you're no longer, you have to account for collisions that are occurring, and we're back to this equation. And even in the observations, you can see that as we come down in altitude, the velocity rotates away from its E cross B direction towards the E direction. And so it's very encouraging, in a sense, to match this up with observations to solidify that. Oh, I guess I was going to zoom in so you can see better. And you can see that rotation as it comes down. Now, we could do the same, given the fact that we have a measurement of the ion velocity with altitude. We have a measurement of the electron plasma drift that's happening in the F region that we assume is not changing as we come down in altitude. We can actually, from the radar data, compute the current. And here's a plot of the current. Also in the background, we can compute the Pedersen conductivity. So these are strong capabilities of an incoherent scatter radar because they can really show you details that, that no other measurement can make. If we look now, I think I look closely at this, and we say, if we look now from the bottom up in a way, before the E cross B was up, and you can see that the current on the bottom is in the negative E cross B direction. So that's a Hall current, and that current is strong down at those lower altitudes, and it rotates back towards the E direction as we come up in altitude. It starts to get a little messy up here. That altitude was about 120, 130, where the differential velocity starts to get small, and you have to have good precision estimates for those quantities to get that right. So it's very satisfying to be looking at the forms of the equations as well as the observations to satisfy that. In the same frame, if we include now neutral winds, the condition gets a little more complicated. We have currents, we have electric fields and E cross B coordinates with Z in this axis. And here's J, the current, the total current. But when you include a neutral wind, now you have to do this vector relationship summations in order to describe what the wind relationship is with regard to E and J. And so when you include a neutral wind, we start to get a little more complicated, and we don't have that measurement. And so we've done some work, or I did a number of things back a while back where I showed these relationships and how you can work through some Joule heating calculations and such using where you can account for some of the neutral wind effects. But it was always indirect, and that's always not very satisfying because we're only going to see a piece of the neutral wind of contribution. And without understanding the neutral wind behavior in this region, it really makes it a difficult task. But let's go ahead and include the winds and into the formulation that we had before. So now I'm including the winds into the equation. And effectively, the equations now look like the plasma motion in the reference frame of the neutral wind is one way to say it. And so we have a V I prime now where we have a differential velocity between the plasma motion and the wind, and we have an E prime, which is E in the reference frame of the neutral wind. We can do that for the electrons. We can also now plug these equations into our expression for current. When we do that, you see that the current that we had before without the neutral wind is the same as the current that we have afterwards. That's a general property of current, is independent of a Galilean transformation or a non-relativistic transformation, and so the current's invariant. In fact, when you look back at that other graph that I had, J didn't change even though we included a neutral wind into the expression because J is invariant to that coordinate rotation. Now if we go ahead and we plug back in our VIs and VEs and we go ahead and we write it all out, we get to the point where we can write out our Ohm's law, which is used quite heavily in the community. And note that this derivation of Ohm's law does have approximations with regard to the plasma motion. I didn't include gravity, I didn't include pressure gradients or other terms. I included only the electric magnetic field influences as well as the collisions and neutral winds. And so this I'm going to call Ohm's law in the neutral frame. And that's written in this form here that hopefully we're pretty familiar with. But the interpretation of that frame, you can come at it a couple of different ways. One way to derive that same equation is to go what's called the generalized Ohm's law. That generalized Ohm's law gives you a time-dependent derivative of the current, and you can go back to your full equations and you can plug it all back in, and you'll have pressure terms and gravity terms, electric fields, current density terms. And what we generally do is we cancel all those things out in order to get our Ohm's law. But it's worthwhile going back to do that because you see what you ignore. And one of the things that Art and Astra have been doing is that they've not ignored the pressure term or the gravity term, and therefore can add additional current regarding pressure gradient effects as well as gravitational effects, in addition to these currents that are associated with collisions and plasma-neutral interactions. Now, an interesting exercise that I've been going through, and I find it to be enlightening, has been if you express the Ohm's law in a different frame. And that means if you start not in our neutral description, but in a plasma description, meaning that if you describe the velocity that you're working under as the plasma velocity, you get exactly the same form of the ionospheric Ohm's law. But now your coefficients, your conductivity coefficients are not the same thing, and your electric field is not the same thing. It means it leads to a different physical thinking about describing this system. It doesn't change J. J is going to give you, you're going to get the same J. It's just that the way you describe it physically is different. And Paul Song has been beating on this for a while, and I think there's some enlightening things that come from that. I think it just takes time to go through it to appreciate what's coming from that. Now, that means then what we should be careful about is when we do say a Pedersen, say, conductivity, that we should say it is in the neutral frame, or at least have a recognition that it's of that form. And one interesting way to describe the Pedersen conductivity is to write it in terms of a mobility by taking these terms and moving them over to this expression, leaving only the mobility terms here. And one thing that you'll find is that you'll get a two-hump distribution. If you did, this is in the neutral frame. If you did it in the plasma frame, you wouldn't get this type of description because it's a different way of describing the process. Here, we see that ions carry the current in the region about 120. And this is the one that we're more used to working with and seeing, largely because the electron density is falling off below 100. And you don't see this secondary peak. But there is, from a mobility perspective, there is current flow down there. And that current flow is in this description, described by the electrons motion. And of course, there's Hall current, Hall conductivity as well. Here's our typical graph when we now include those mobility factors along with the electron density, and you can get this description of what we usually use in describing the Hall, Pedersen, and the parallel conductivities, which are so important for either our drags or our electrodynamics. And so we get our typical descriptions of Hall conductivity peaking below 120, Pedersen conductivity. And a lot of this behavior, though, is related to the electron density, as you can see, in how it behaves. But there's also a neutral density contribution to describing these that need to be accounted for as well, which we don't have a good measure of, and we usually use EMSIS or something like that to provide us with description of the neutral. So this leads me into a discussion on, largely we've been talking about momentum and electrodynamics, but it also applies obviously when we're deriving our equations for heating. So again, in terms of what I've been emphasizing, depending on how you define your system of equations will determine how you physically interpret them. If we use the individual species equations, meaning that I have a neutral wind description, an ion description, electron description, we can do like I did with the neutral momentum equations, I can write an energy equation. And with the energy equation, I'm only going to include the terms that are associated with the frictional heating description. There's other terms, of course, to this equation. But this is the neutral energy equation where we're concerned about the work being transferred to the gas in the form of heat by the frictional interaction of neutral gas with plasma, as well as the heat transfer that occurs because of the differential temperatures between the plasma and the neutrals and the collisions that try to thermalize them. And so these are just straight up energy definitions. In the ion energy equation, it's been shown that it can be simply equality between the temperature differential and the frictional heat. But be careful in how you say frictional. If you just say frictional heating, you have to say which one you're talking about because they are absolutely not the same thing. So if we stay with the neutral the neutral energy equation, but we take the ion energy equation and we say, hey, we've got this expression for Ti minus Tm. Why don't we just go ahead and toss it in there, and then we can break this equation down a little further. We use a little bit of momentum conservation between collisions to switch some collision frequencies around. And we get an expression that some people use to call the neutral frictional heating rate. And that is one where the differential velocity squared gives us the total energy here of how much energy has been transferred to the neutral gas by frictional heating as well as by the temperature differential. So we get this, but it looks like it's just frictional heating. It doesn't really look like you still have this going on, but you absolutely do. It's because we've done this step here that makes it look like we're just accounting for differential velocities. You have to be careful about that as well in doing your expression, and Josh and I have describes this in a paper back a while ago. Now, with that, let me step to Joule heating. Now, I'm going to use, again, Joule heating in the neutral frame, because we should be careful about what frame we're discussing. And the challenge with Joule heating is that you don't see Joule heating in the expression for the individual energy species equation. That's because Joule heating is really a single fluid MHD description of how much total energy content due to this process is going into the gas. And that gas is a single fluid gas whose gas is weighted by the mass relevance of the neutrals, the plasmas, together. In our domain, in a highly collisional gas, it's usually the neutral gas that's equal to the weighted average gas. And so people, we tend to say this Joule heating rate is in the neutral frame. Now, a step that people take is they say, well, okay, we use this a lot, and we throw this around a lot. I really do think we need to be careful of how we toss this about. But then we also say, well, let's see how we can relate this to the individual frame. So I'm going to plug in my expression for J that I had before. I'm going to just do this expansion stuff that we did earlier on. You could show that this is equal to sigma PE prime squared. So that's reassuring, because a lot of us use that as well for an expression for Joule heating, and it's equivalent, and that's cool. Now, KE is in here, and that one's where you're worried about the gyro frequency to the electron neutral collision frequency. If you look at that diagram back a while, that relationship, KE is very large, above about 80 kilometers. So it's not until you get below 80 that you have to worry about this term. So we're going to drop that guy, and we're just going to go ahead and keep the ion term. Now I'm going to continue to march through, and I'm going to say, don't forget that we set up these ion velocity momentum equations. I can write it in this form. I can solve for E squared over B squared, which turns out is necessary to be plugged into here. I can then compute the Joule heating, the Joule heating rate into this form here. And as you can see, this Joule heating rate that I just derived is the same one that I derived in the previous slide on the individual species description. This is fortuitous, but can be very confusing, because one is describing the Joule heating rate for the total energy input into the gas, and the other one is describing the energy input into the neutral gas. And it's because that the reference frame that we're describing here, that weighted frame is so heavily weighted to the neutral gas that they come out to be equivalent, but their physical description are not. And you have to be careful with that. I have to say that sometimes in my writing I wasn't always as careful as I think I should have been. Now if we talk about Joule heating a reference frame, Vitenis has been getting on us for a little bit about our usage of these types of descriptions. And I spent a lot of time thinking about these kinds of things as he published this paper in particular. And I finally got to grips with it after a while, in that one thing that they do right off the bat is they say, why do you work in the neutral frame? It should be done in the plasma velocity frame. And that's, again, coming from a plasma physicist perspective, meeting a hydrodynamicist perspective. And that can be confusing, because it's not always that the two communities are equally on the same plane. So when you look at the heating rate that they describe in the electric field in the plasma frame, not in the neutral frame. And they derive this expression here, which also can be written in this form here. That guy right there leads to a lot of confusion within our community and that community, as well as the solar chromosphere community. Because that guy right there is what they call as classical Joule heating. And classical Joule heating has they use resistivity instead of conductivity. And the resistivity expression is something like this. Nothing like what we've really described in our description of Joule heating or Pedersen conductivities in describing our Joule heating rates. But that's because we do it in the neutral frame and they do it in the plasma frame. Now it turns out that this resistivity is very similar. You can see this, here's my case of E, but it's much less than 1 because this is 1 over case of E. And so that term goes to 0. And so in the end, when Vitenis derives this expression, they get the same answer that I just got a slide or two ago using the neutral wind frame. So, and that should be fine, because the frame dependency should give us the same, you should get the same answer out, but the physical description can be different. And I've had a lot of discussions with people about it, and it is challenging unless I do what I'm doing to you today. It's just pouring through it and trying to get you to see where we're coming from. Well, this really spawned from a LWS workshop that we had with the solar chromosphere. Solar chromosphere is a part of the solar atmosphere described here. It's interesting if you look at the temperature profile, and it's interesting, they do it radially instead of vertically on their scales when they display things, which I think is fun. That was also a point of contention. So you have a minima here in the photosphere, that then it transitions to increasing temperatures, and then eventually you get to the transition region into the corona. And this is the domain, if anyone's interested in the solar, when we're looking at the photons coming from it, it's out here above the 175 domain or so. I'm sorry, around the 150 nanometer wavelength band. But from a gas plasma perspective, we got together, and James Leake, Rick DeVore, myself, and a bunch of others who were on this, who were in the CEDAR community, got together, and we did this study. The study was to look at solar chromosphere and ionosphere-thermosphere behaviors to see what kind of comparisons and equivalents. And I worked a lot with Rick and James on this paper. It took us quite a while to slog through it all. And one of the things that you may not even realize, you think the sun is so hot, it's 10,000 degrees, so it's 1,000 degrees, the chromosphere, so it's 10 times hotter than Earth's upper atmosphere. But if you look at the comparison between them in terms of neutral densities and electron densities, you find the definition of weakly ionized gas applies to the chromosphere. And so all the things that we just talked about, weakly ionized gas for the upper atmosphere, can actually be used in the chromosphere. Now, there are obvious caveats, like the magnetic field is going crazy in the chromosphere, and our magnetic field is not. But it is interesting to look at the two and try to apply it. And fundamentally, if you look at the plasma-neutral collision relationship, and now this is the same type of curve that I showed earlier, the relationship of ion-neutral and electron-neutral collision frequencies to the gyro frequencies. And you do the same in the chromosphere, and you can identify regions, Pedersen, Hall, and E cross B, plasma drift regions, that apply in the chromosphere. And this band here for the gyro frequencies is accounting for the fact that the B field is changing so significantly. So when you plug it in and you look at your mobility term behavior, and this is what I showed earlier, we get our nice Pedersen mobility, and then you multiply that by whatever the electron density is for that time, and you can get it, the conductivity out, and you get your Hall descriptions. We get the same shapes, and we can focus maybe only on the solid curve. This is the Pedersen. There's kind of a two-peak hump here. Realize that the chromosphere is mostly made up of hydrogen, so we're dealing also with a change in mass that's more like 30 to 1 between the Earth. So that kind of compensates for the temperature difference when doing scale heights and things like that. And so you get the peaks here. You get your Hall conductivity as well. And so in the end, they're describing processes really in a similar manner to the way we describe. They're using single fluid approximations, so therefore their expression for Joule heating, which again, I showed you last time, was resistivity times this. You can also write it as the conductivity, the Cowling conductivity. You can calculate that Cowling conductivity inside the chromosphere, which lies in this domain here. You can see that there's a high Cowling resistivity, and that therefore you expect strong Joule heating. And there's been a number of papers, and this is a nice one that by Goodman, that shows us how the chromosphere and processes within the chromosphere lead to things like Joule heating. And then in the paper that we did, we tried to, and it took a lot of time, and part of what I'm showing you today is a number of years of discussion about coordinate systems and all that good stuff to get it straight. So let me summarize. I don't know where I am on time. Maybe I'm doing okay. So first, as I mentioned, define and know your coordinate system and your reference frames. And this is not just for modeling, but it's also for just interpreting your data. And to make sure that you can use it more universally, I want to see us being able to be a community that can apply to discussions with solar physicists about chromospheric or stellar chromospheres. I want us to be able to discuss with planetary systems, on the same plane, because it's very difficult to have those discussions when you're in different reference frames and you don't even know it. That's the worst part of it, because then you just completely confuse discussions. And I refer to James' paper. He did a great job of working on that, and it was a really great experience. And a number of you in the room were here, and it was a great time to work through that. I just have a few things just to comment on summary. You know, in using your ionospheric Ohm's law, you know, nothing about it can be causal. We can only say that if there's a linear relationship between a current and an electric field, and those relationships the proportionality constants are defined by those connectivities. But it depends on what reference frame you're in as to what those connectivities are. And so just keep that in mind as you're moving along in any kind of electrodynamics that you do. And also, I think that in general, I think the frictional heating description is very clear and lacks any type of ambiguity, except that if you don't say which species you're talking about, that could be confusing. So you need to say if it's neutral ion or electron frictional heating. But I think that's the most straightforward. You can use, as I mentioned, you can equate Joule heating to frictional heating, and there's a bunch of approximations that get us there, so you can do it, but you just have to be aware of how you're using it. So I think we should be careful about that in the future. And then finally, just with challenges that I think the plasma neutral interactions remain, is that we're absolutely missing energy in the MI coupling problem. The connectivities are just not adequately being described, no matter how hard Ryan McGranahan tries to do that. I think it's still extremely difficult because of the multi-parameter requirement to describe the connectivity. And so we're missing that, and we really need to do a better job in trying to provide an estimate of connectivity, which relies on electron densities and neutral densities. We're also lacking an ability to transform that energy that is coming in, that we have, into forms of energy within the IT system where it's being distributed in terms of momentum or heat. And a lot of that has to do with the fact that we have insufficient descriptions of neutral winds in this domain. We don't have there's challenges in how the dynamo process is being modified, either by from forces from below or above. Again, I think it's tied back to the neutral winds, coordinated again with plasma measurements. And then overall, in this MLT-X domain, in the 80 to 200 kilometers, we really have limited profiling capability in the neutral side. I think the ISRs do a phenomenal job of that measurement. But on the neutral side, we're heavily lacking. And it's the most, in that domain, it has the greatest gradients in every parameter that we can think of. And it also is a region where most of our energy is deposited. So it's a key region. I think I'll just leave. We're having a workshop about this grand challenge right after the break, and I think I'll stop there. Thank you.